Hello everybody again. Today we are going to continue with the third section on sets. Again, Star Academica is presenting this for you. If you have any questions, suggestions or remarks, please email to the following email account staracademica@gmail.com. Okay, what are we going to learn today? Ordered tuples, Cartesian product of sets, operations, we'll see union, intersection of sets, difference, complement, and some other examples. Okay. First, in order to define Cartesian product sets, we need a couple definitions. We are going to define ordered and tuples. What does an ordered tuple first mean? An ordered tuple with an order in which the first entry A and the second entry B is located looks like the following. So we have open parentheses, we put the first entry separated by a comma, B, and we close the parentheses. Okay, so this is how a tuple looks like, and the order is important. So this is different than sets notation. We could put three entries next to each other like A, B, C in order. So again, we use parentheses and we put A, B, C separated with a comma. This is called a triplet. Further, we can generalize this notation to n-ordered tuples. So we can put n entries in order. Again, we use parentheses and put A1, A2 up to AN in an ordered fashion, where A1 is the first entry, A2 is the second, etc. Let's look at an example. Since the order is important, if we have 1, 2, 1, 2, this is different than 2, 1. So they are different things, because in the first position we have 1 here and 2 here, so they are different. If two tuples are equal, like A, B is equal to C, D, then the first entries must equal to each other. So A must equal to C, and B must equal to D. So this is both ways. It goes this way. If you have two tuples equal to each other, then we have AC is equal to B, A2 equal to C, B equal to D, and vice versa. If A is equal to C and B is equal to D, then the tuples are equal, which is trivial. Now it's time to define a Cartesian product of two sets A and B, and the notation is like A times B, or A cross B. So what is A cross B? It is the collection of tuples A and B, ordered tuples, where A comes from the first set A and B comes from the second set B. Okay, let's first have an example. If we have two tuples A3 and 2B equal to each other, and the question is, what is A plus B? Okay, from the definition of equality, A must equal to 2. So the first entries must equal to each other and the second entries must equal to each other. So A is 2 and B is 3. And the question is, what is A plus B? Then it is 5. Okay. We continue with the examples. Say we have a set A, 2, 5, and set B, which consists of A, C, and D as elements. A cross B, so we going to construct tuples. Okay, tuples where the first entry comes from the set A and the second entry comes from the set B. So let us keep an order. So we are going to take first 2 from the set A and compose all possibilities. So 2 is matched with the A first to get 2A. So here it is. We match 2 with the C, we got 2C. We match 2 with the D, 2D. So these are all possibilities starting with the 2 in the first position coming from the set A. Now we have another element from set A, which is 5. It So in the first position we have 5. We match 5 with A, so we get 5A. We match 5 with the C, and we match 5 with the D. So these are all what we have. Actually, we are going to see the size of the A cross B, but from here, as we construct it, should be clearer. So how many copies of B we are really having? With this entry, we have 1 copy of B, which are 3 elements. So we have 3 elements contributed to the Cartesian product, and for 5 we have another 3 elements contributed to the Cartesian product. So altogether there are 6 of them. So 1 3 2 3, so this is 2 times 3, which is the number of the elements of the new set A cross B. Okay, let's continue. Suppose C is a set with a star and a 1, 2 elements. D is a set with a bullet and alpha. So C cross D, so we take star with the bullet. Here we go. We take star with the alpha. Great. Next we take 1 with the bullet. Perfect. Again we take 1 with the alpha. So these are all. How many elements do we have? 2 for C, the size of C, times 2 for the size of D. There are 4 altogether. Let's look at another example. This time the question is to list down D cross C. So we have C cross D. Now we want D cross C. One may think that they are equal, but this is not the case in general. As we are going to see now, the first entries from this Cartesian product come from set D. So now we start from D. We match D with a star. Here we go. We match bullet with a 1. We have it. Next we match alpha with a star. Here we go. And we match alpha with a 1. As we compare these two sets, they are not equal. And in general, this is the case. So D cross C is not equal to CD in particular problem, but in general, this is also true. We can say more about this non-commutativity. So we cannot change the places of the sets when we take the Cartesian product, since the order matters. A not empty, B is not an empty. Then if A is not equal to B, then A cross B is not equal to B cross A, and vice versa. If A is equal to B, then surely the cross product of these two sets, they are equal. So this is a trivial case. It's like because A cross A is equal to A cross A. Nothing strange here. Here is another example regarding the size of the product sets we already mentioned, but let's do one more example and then put down the formula. If A is 1, 4 and B is x, y, z, t, then A cross B, again, 1 is matched with the x, 1 with the y, 1 with the z, and 1 with the t. So here is what we have. These are matched by 1. And 4 with x, 4 with y, 4 with the z, and 4 with the t. And we have 2 more. So we have 1, 2. This is the size of A. And in each block, we have 4, which is size of B. So this is 2 times each block 4, which is 8. So A cross B, the size of the A cross B, the cardinality of A cross B is 8. Here is a formula. If A has n elements, B has m elements, then A cross B, the product, the Cartesian product, has size n times m. One can go further and also define Cartesian product of more sets. For example, in general, if you have n sets, A1, A2, An, and each is non-empty, okay, and then the Cartesian product of these sets is going to be the collection of all n-ordered tuples. Collection of all n-ordered tuples. Let's have an example. Say we have a set A, 1, 2, B, X, Y, and C, A, B. So what is A cross B cross C? Okay, we need to be careful and follow some steps. Say first we are going to construct all elements of A which start with a 1, but this is going to match with B cross C. Okay, this is the trick. So now we construct B cross C, XA, here we go. So 1 with XA, XB, here we go, 1 with XB, We are not done. Remember, y with a, great, and y with a b, perfect. So this is all with the ones from a. Okay, so now we have 2. For the 2, again, we have b cross c. We do the same thing, xi, xp, y. You can copy it from there. So these are all the elements. Okay, so we can make this, generalize this for 4 sets or 5. It's the same idea. Another example is about a square. What does a square mean? It is a cross a. And what is a cross a? Again, you put a copy of a next to it, and you start making up the tuples 1, 1, 1, 3, 1a, and we are done with 1, so we start with the 3, 3, 1, 3, 3, 3a, and then we start with a1, a3, and a. Here we have all of them, because a has 3 elements. This has again 3 elements. Altogether, the new set, a square, has 9 elements. They are all listed here. And if a is a non-empty set, a to the n copies of a. Here we have 2 copies of a. We can generalize this to n copies. So there are just n tuples, all possible ones. Each entry is coming from the same set a. Okay. Let's define the relation, but we are not going to do more than this in this section. We are going to have a new section in the future where we are going to deal with this important topic. So what is the relation, and what does this have to do with a Cartesian B? It is a non-empty subset. So R, you take a non-empty subset of A cross B, and this is called relation. So R is called a relation. Let's look at an example. Say we have a set A with the 2 elements, vegetables and fruits. Set B with the 3 elements, apple, bananas, carrot. So A cross B will have 2 times 3, 6 elements. However, we take a subset with the 3 elements. See, 1 element, a subset of A cross B, 2 elements and 3 elements. And you see vegetables is related to carrot. Here we go. This is tuple. And fruits with apple and fruits with bananas. Actually, this makes sense from real life situation, because vegetables, carrot is a vegetable, apple is a fruit, and bananas is a fruit. Okay, we'll see more in the future. Operations on sets. The first one is the union. So we can unite 2 sets. Given 2 sets A and B, if we put together all the elements from A and from B into 1 set, this new set is called A union B, and this is the notation that we call union. Okay, so X is an element such that X is in A or X is in B. It could be in both, really. So with Venn diagrams, this is the set A, the set B with the red, and the A union B is do everything inside these 2 sets. Here's an example. Given a set A with the 1, 2, 3, 4, 6, 7, and a B with 6, 7, 8, 9 as elements. The question is, what is A union B? Let's picture them in a Venn diagram. Here is the set A and set B. Here 6 and 7 are in common, so they belong to both A and B. This is how we picture them. And extra 0 and extra 5 are outside of A and B. However, we have a U here, you see a rectangle. So this is a universal set. So we are going to see this U oftenly. It is called universal set. Everything lives like the universe that we are living in. All objects are in the universe. So what is A union B? Everything that you see inside A and inside B, which is A union B, it's 1, 2, 3, 4, 6, 7, 8, 9, as you see. So we are not going to double count 6 and 7 in the sets. As we mentioned before, this is not quite possible. There is no order. And 0 and 5 are outside of A union B, so we do not include them. This is it. What about the intersection? Another important operation on sets given A and B. The elements which belong to both A and B Okay, so x is in A, this has to be V, and that's my mistake. So we have Vx in B. So A intersect B intersection, we use the upside down of U. So this means intersection. So with the Venn diagrams, if you have A and B, this part which belongs to both is the intersection. So A intersection B. Let's look at the example. Again, given A and B, what is the A intersect B? So it is this part. What do we see in both 6 and 7 belong to both sets, A and B, so the intersection is 6 and 7, so the size is equal to 2. Disjoint sets and the size of A union B. If two sets have no common elements, then they are called disjoint sets. So if A intersects B is empty, then A and B are disjoint. If A and B are disjoint, A intersect B is empty. Let's look at this example. Say A has 1, 2, 3 as elements, B 6, 7, 8, 9 as elements. Do we see anything in common? No, they have no common elements. So A intersect B is empty. So we say that A and B are disjoint sets. Another important formula, actually maybe this is so far we have this only one, is about the size of A union B. So the size of A union B is the size of A plus the size of B minus the intersection. Why this is the case? Let's look at these Venn diagrams. It should be clear from the picture. So the yellow one is the size of A, right? Everything here is in A. If you plus B, you got the green part also. What's happening really? So in between, the part in between, which is intersection, is overcounted, actually double counted. If you are adding this 2, this is more than what we need for the union. We have this part, the intersection part, double counted. So we need to subtract one copy. So we have A and B minus A intersect B. So this is a very important formula for sets. Let's use this formula in an example. The number of students in a class that can speak only French is 3 times greater than those who can only speak Spanish. So say as the set of Spanish, give a number, call it X, many students. The set of the students who speak French, 3X. This is what it says, really. So people who speak Spanish S, people who speak French F. The number of students that can speak both languages is equal to 10. So the students that speak both languages, so S intersect F is equal to 10. There are also 5 students that can neither speak French nor English. So outside of S and F, we have 5 more students. Well, keep this in mind. And altogether, in the total, the number of students is equal to 65. So the question is, what is the number of the students that can only speak Spanish? So what is X really? Okay, here is our diagram. So S, call this S, call this set F, and what does the question say? It says that we have 10 students who speak both French and Spanish. Great. We have 3X students which speak only Spanish, right? Is that true? Okay. That can speak only French is 3 times greater than those who can speak Spanish. So here we have something strange. So we are going to make this X here and this 3X, right? People who speak French are 3 times greater than those who speak only Spanish. So the green one is only people only speaking French. So French is 3X. Spanish, the yellow one, is just X. Intersection is 10. Students outside, they are 5. And altogether, 3X plus 10 plus X plus 5 is equal to 55. So we have 10 and 5. We can move to this side. That's going to be 40. We have 3x plus x, that is 4x. So 4x is 40, x is 10. So remember we did change this. This was really 3x, and this was really x. So people who speak only Spanish are 10. People who speak French, so this is S really, and this is F, will be 30. So we have what we wanted. Okay, difference of sets A, difference B. The set of elements that belong to A but not B is called the difference sets of A and B. So here is a common property representation, x in A but x is not in B. Okay, let's look at this example, 1, 2, 3, 4, 5, 6, and B, 4, 5, 6, 7, 8. So x in A, the elements which are in A but not in B, so 1, is 1 in A but not in B? Yes. 2, yes. 3, yes. 4, it's in B, so we don't take it. 5, it is in B, we do not include it. And 6, it is in B. So the only elements which are in A but not in B are just 1, 2, 3. With a Venn diagram, this is A difference B. So A difference B is A union B. A union B, you can think this way, that is A union B. You subtract B, so that's the difference. A union B, again A difference B is x in A, and x is not in B, another way of representing. So there's also, in some books, textbooks, we see A minus B for difference. This is also okay. So if you see this, it means A difference B. And B difference A is this part, right? In B but not in A, just this part. And what was this? This was A union B, right? Intersection. So from here we can do what? We can say that A union B, this is interesting but important. What is A minus B? Right? Union A intersects B. Union B minus A. So A union B has 3 parts. This part, A intersect B, and B minus A. So there are many ways of representing what we have seen before. The complement of a set, another important notation. To define this correctly, we need to make sure that we know the universal set. So the universal set must be given to us. And a set A is given. So what is the complement of A? The complement of A is everything which is outside of A. Elements which do not belong to A. So this is the notation. We put a bar at the top, over line, or bar at the top of A. So this is called A bar or A complement of A. X in the universe, it's the universal set, but X is not in A, or universal minus A. With a Venn diagram, so the white part is the set A, and the complement is outside of A, but we have a border, so you need to know what the universal set is. So here is like a rectangle, so anything outside of A. So the blue part is A complement. Let's look at an example. Let the universal set U be X and natural number. Natural numbers start from 0, right? 1, 2, 3, 4, goes like this up to infinity. But the set U is X less than equal to 10, so including 10, the set U is this set. Okay, so what is then A complement? A, if A is equal to 6, 7, 8, 9. It is the universal set minus A. So you take the universal sets from 0 to 10, so we exclude 6, 7, 8, 9. So we end up with 0, 1, 2, 3, 4, 5, and the 10. So that's the complement of A. Let's look another example. Suppose that A is the set of sophomores at your school, and B is the set of students in discrete mathematics at your school. Express each of these sets in terms of A and B. So the set of sophomores taking discrete mathematics in your school, it's A intersect B, because the students are sophomores and taking discrete mathematics, so it's the intersection, belong to both sets. The set of sophomores at your school who are not taking discrete mathematics. So you have the set of sophomores and the ones that are not taking B. So A intersect B complement, right? The ones that are not taking discrete mathematics are B complement. And both of them, sophomore and not taking discrete, it's intersection. And this is A cross A minus or A minus B. Just the same. A intersect B complement is A minus B. The set of the students at your school who either are sophomores or are taking discrete mathematics. So A union B. Either they are sophomores or taking discrete mathematics. And the last example is the set of the students at your school who either are not sophomores, okay, not sophomores, so this is A complement, or union, not taking discrete mathematics, B complement. When you say or, it's union. Okay. So as we see, we have built notation that we can express many words, many sentences in a simple mathematical symbolic way. So this is a nice example of set theory. So we can communicate. We don't have to use many paragraphs, many long sentences. We just define first what is A and B, and then we can use the notation symbols to represent the stories. Set operational identities. That is going to be our next topic. So we are gonna stop here, and I'll say goodbye to everybody and hope to see you in the next lecture.